Future dynamics problems are going to be much more complicated than the simple elevator problem we just did. So I'm going to repeat it with a protocol for solving more complicated dynamics problems, and we're going to learn this dynamics protocol and use it a lot. When we first look at a problem, we always try to find the underlying physics concept or develop the lens. So I'm going to call this the zeroth. Lens identification. So the first thing we want to do is look at the problem. We have an elevator and we're standing on a scale. It's accelerating upward at 2 meters per second squared. And we want to find the reading on the scale, which I know is the normal force. So I'm going to label the normal force there. So let's say we want to try the dynamics lens. My motivation for that is, I have forces, I have the normal force and the force of gravity, and I have acceleration. Yes, when we're dealing with forces and accelerations, we want to try the dynamics lens. The next step is to recognize, wait, well, I may not know the formula for answering this question. I know the general formula is going to be the vector sum of the forces is equal to mass times acceleration. Now that we have this as our foundation, let's identify the forces and their directions. Let's identify the acceleration and its direction. Already I can see I've done a pretty good job. I've made a free body diagram without even thinking about it. And so the next step would be to build my free body diagram. Why? To identify the forces and identify the acceleration. So I know that the normal force is upward on me, the force of gravity is downward, and then over here, I identify the acceleration. I don't put it on here because the acceleration is not a force. The forces produce the acceleration. Then I want to add these forces to get this acceleration. So I'm going to add these vectors. So I can take my normal force and my force of gravity, and I add them together to get the vector sum of the forces. Oh wait, that's not how you add forces. You add forces nose to tail, of course, right? So if we have a force pulling up, and I want to add the force pulling down, I add the nose to tail, and now I have the normal force plus the force of gravity. And the vector sum of the forces I put with a double arrow is here, which is great. But now what I can see is, hold on, the vector sum of the forces is in the same direction as acceleration. So I look, wait, my acceleration is upward, but I've added these, so the vector sum of the forces is downward. And what I realize is, yeah, I have to make this normal force much greater. And if I did, if the normal force were greater, now when I add that normal force to the force of gravity, from the very beginning to the very end, we can see now I have an upward vector sum of the forces. So now I can put these numbers into this equation and solve for the normal force. So I can write this, the vector sum of the forces is mass times acceleration, and I have a normal force plus the force of gravity is equal to mass times acceleration. So the normal force plus the force of gravity is mg is equal to ma. Now before I go any further, I've made a crucial mistake, and that is I haven't identified positive or negative. I haven't identified a positive direction. And so what I'm going to do here is I'm going to say this is the positive y direction, and I won't worry about x direction because nothing's happening there. So now we can identify this as a positive force, a positive acceleration, and this is a negative mg downward. And so this goes here. Now I can solve for the normal force and see that the normal force is equal to ma plus mg. And that's equal to 70 kilograms times 2 meters per second squared plus 70 kilograms times 10 meters per second squared, or 140 newtons plus 700 newtons is equal to 840 newtons. Now we might reflect, if I was in equilibrium, if this was moving up or down at a constant velocity or at rest, then the acceleration would be 0, and yes, the normal force would be equal to the force of gravity in the opposite direction. And if it were accelerating downward, like for instance, the elevator is moving up but slowing down, there'd be a downward acceleration. And then the acceleration would be negative, and this would be only 560 newtons. And my drawing would be different, right? My drawing would then look like I originally drew it, where the force of gravity would be bigger than the normal force. And so the vector sum of the forces would be downward. So what did I do? I recognized the lens. This is a dynamics lens because it's dealing with accelerations and forces. I wrote F equals ma, the vector sum of the forces is mass times acceleration. I identified those forces and the acceleration in a free body diagram. And then I added those forces as a vector, nose to tail, to give me the vector sum of the forces. Then very importantly, I defined the direction as positive and assigned the signs and filled in the equation to get my answer. We're going to see very complicated problems in the future and in engineering much more complicated, but they all follow the same protocol.